all over x dx, expanding this between the interval 0 and 1. Between the interval 0 and 1. So we said what to do here. Please mute your mic. Muslima, I said 10 o'clock. I said 10 o'clock, please. Log out. Muslima, I said 10 o'clock. So sin x over x dx now is what we are going to expand. The thing is like this now. Please be very observant. We expand sin x at point 0. If we are to expand it at point 0, so which rule are we using? See the Maclaurin's rule, Maclaurin's theorem, or the Taylor's theorem? Taylor's theorem. Anyone? If I were to expand this function sin x like this, am I going to use the Maclaurin's theorem or the Taylor's theorem? Can you hear me? Hello?
We'll use Maclaurin's theorem.
If you can hear me, just let me know. Even if you are not willing to listen, just let me know if you not hear. So sin x is equal to x minus x raised to x minus x raised to power 3 all over 3 factorial plus x raised to power 5 all over 5 factorial minus x raised to power 7 over 7 factorial. This is the expansion of sin x. If you use the Maclaurin's theorem, so use the Maclaurin's theorem yourself. This is the expansion of sin x to infinity. So I've expanded sin x now. Now let me write sin x all over f. That's going to be all these things that I have here divided by x. So because they are connected with the operators plus and minus, I have to be doing x all over x plus minus x cubed all over 3 factorial x. I'm dividing everything by this x. So I have to divide this term by x separately, divide this term by x, divide this next term by x. So plus x raised to power 5 all over 5 factorial x. So I'm stopping here. Infinity. I don't want to write my 7 raised to 7 x raised to power 7 again. So the integral now becomes 1 between 0 and 1. Sin x all over x is now equal to the integral of x all over x is 1 between 0 and 1 minus x in x cubed. That is, x cubed is x times x. So x in this, that's x here 1, x here. So I have x squared left. So that's x squared all over this 3 factorial plus x raised to power 5 divided by x means x raised to power 4 all over 5 factorial to this infinity. So I have to integrate now, because if I do not integrate, there is no way I can take off this sign, right? So now you have to be very, very observant. How do we integrate this concept? So look at it very well. So integrate this now. If I want to integrate 1, I have to get x. The integral of 1 is x now, the variable, minus the integral of x squared is x cubed all over 3. This is it. This is x squared. The integral of x squared is going to be x raised to power that square that is on it. So 2 plus 1 all over the 2 plus 1 down here. This is how to integrate. So this is x raised to power 3 all over 3. So this is x raised to power 3 all over 3 times 3 factorial that is here before, plus x raised to power 4 will become x raised to power 5 all over 5 times this 5 factorial that is here already. So we now have the boundary. We've integrated it, but there is the boundary between 1 and 0. So to get a value for 1, that's going to be x minus, let's simplify first, x minus x cubed all over 3 times 3 factorial. That's 3 times 3 factorial is 6 plus x raised to power 5 all over 5 times 5 factorial gives me 120 between the interval 1 and 0. So I have to use the value of 1 first, then use the value of 0 later. Taking the value of 1 first, that's 1 minus 1 raised to power 3 all over 3 times 8, 3 times 6 rather, 18, plus x raised to power 5, that's 1 raised to power 5 all over 5 times 120, 600. So minus to my infinity. So this is the value when I'm using 1 minus the value when I'm using 0. That's 0 minus 0 raised to power 3 over 18 plus 0 raised to power 5 over 600. You know, everything here apparently gives me 0 because 0 minus 0 plus 0, that's 0. So I'm not concerned about that again. What I need to do is to evaluate this function, is to simplify this arithmetic I have here. 1 minus 1 all over 18 plus 1 all over 600. So doing my mathematics here, I don't even know what I'm doing. I don't know. Please let me do it. 1 minus 1 divided by 18, anyone do? One divided by 18.
Please, your audio is low. No.
My audio is low. Are you hearing me like this?
Yes, I can hear you.
1 over 18 is what? Kilogram. 0. Okay. So 0.055 plus 1 over 600. Yeah, be like 0.0017. So now it's going to be 1 plus this minus this. So I have 1.0017 minus 0.055. I'll be like 1.0017 minus 0.055. 1.0017 minus 0.055. Hmm?
0.947.
0.95.
947.
0.947. So this is the value using this series expansion method. We've been able to evaluate this integral using that method. So that is that. You might be asked to solve that of cosine x all over x dx between 1 and 0 or between 1 and 3, anything you want to use. Just expand it, function this way, and you do the needful. That's that as per this. So the next thing which I'm going to stop there is the L'Hopital's theorem. So how do we use the L'Hopital's theorem here now? L'Hopital's theorem says that it is stating that if we have two functions in each other, that is my own f of x equals my f of x is equal to or something. Let's say I'm having something. Let's just say a is equal to limit x to something. Let's say x to small a. For the function f of x all over g of x. I have two functions, one at the top, one below. So what is the value? How do I do this? Actually, they use L'Hopital's theorem for indeterminacy. When I have 0 over 0, or 0 over infinity, or infinity over 0, or infinity over infinity. That's where we use it for. That's what we use it for, actually. But we use it now with people have extended its use. So here now, let's say I have a function a is equal to sine Abdullah and get red pen. sine x minus cosine x all over 8x squared. So this is a function. Now limit x to pi. Let's say this is a problem that you're asked to solve. So how do you use the L'Hopital's theorem? L'Hopital's theorem is telling you that if you have something like this, then you should keep differentiating. Differentiate f of x to be f prime of x. Differentiate g of x to be g prime of x. Keep differentiating until you get the denominator to a point where it will only turn to undefined. It will only become undefined if you differentiate it. So now let us use this one we wrote here as the example. A is equal to sine x. A is equal to sine x minus cosine x all over 8x squared. What do? We write limit x to pi. Differentiate sine x, that is cosine x, minus differentiate cosine x, that's minus sine x, all over differentiate 8x squared. 8x squared is 2 times 8, 16. X raised to power 2 minus 1, that's 16x raised to power 1, that's 16x. Then we go again, limit x to pi, because I still have 16x here. If I limit x to pi, I'll still be writing 16 times pi. I don't want to do that. Let me keep using the L'Hopital's theorem. So now I'm having the derivative of cosine x is minus sine x minus derivative of minus, okay, this is minus times minus is already plus, Abi. So derivative of sine x now becomes cosine x, right? All over derivative of 16x. Differentiate 16x, that's going to be this ordinary 16. Now I've arrived at 16. If I differentiated the numerator now, it's still differentiable. But if I differentiated the denominator now, it will turn to 0 because the derivative of a constant is 0. If that happens, it renders the whole situation undefined. I don't want undefined. So I have to stop my differentiation here. Now let me evaluate. This can also be written as limit x to pi for cosine x minus sine x all over 16. Because minus sine x plus cosine x is the same as plus cosine x minus sine x. Minus 3 plus 4 is the same as 4 minus 3. So we can now evaluate now. This is cosine pi minus sine pi. So this is cosine pi minus sine pi. So all over 16. So what is cosine pi? I said if pi is, whenever pi is accompanied by cosine, it becomes 180. Cosine pi means cosine 180. That is minus 1. Minus sine 180 is 0 all over 16. So the value of the limit of this function as x approaches pi is going to be minus 1 all over 16. Any question on this before we try another example? Anything you do not get, please let me know now. Before we try another example. Any question? Okay. So let's now do this. This now, like when we were doing comparison test, when we were doing convergence test, you might be encountering some things that will be hard for you when you are doing this to infinity. Maybe it can help you if you could use the L'Hopital's theorem somewhere. Just that it doesn't really work in most cases for infinity. So let us do this. Limit x to 3 for x cubed plus 7x squared plus 9x minus 3 all over x squared plus 2x. Please, everyone, let's do this together. You might be like, I want to evaluate this limit. It's stress. This one may not even stress you with the normal replacement theorem. So let's do this one with this L'Hopital's theorem first. Then we look at one that can stress you with the normal replacement theorem, and you evaluate that one without stressing yourself with the L'Hopital's theorem. So this is going to be limit x to 3. Let us differentiate. X cubed becomes 3x squared. Still write your limit x to 3. Plus 7x squared becomes 2 times 7, 14x. Plus 9x becomes 9. All over x squared plus 2x. X squared becomes 2x. And 2x becomes 2. So this is limit x to 3. Again, we differentiate. We keep differentiating until we don't have any x under it again at the denominator. So differentiate 3x squared, that is 6x, plus differentiate 14x, that is 14. All over 2x plus 2. Differentiate 2x, that is 2. Differentiate 2, that is 0. Now, if you keep differentiating, you'll be having 0 underground at the denominator. So to avoid that, just stop your differentiation now and use the replacement theorem straight. That's 6 times 3 plus 14 all over 2. So this gives 18 plus 14 all over 2. And that gives us 16. So that means the limit as x approaches 3 is 16. So what about something like this? X squared minus 8x plus 72. X squared minus 8x plus 72 all over x minus 2. Limit x to 2. If you encounter something like this, don't stress yourself, bro. Just use the L'Hopital's theorem. What do? You know, if you come and use the normal replacement theorem, replace x using 2, you know it is already 2 minus 2. It renders everything undefined. So what happens? Use the L'Hopital's theorem. Differentiate the denominator, differentiate the denominator. Limit x to 2 then. X squared becomes 2x. Minus 8x becomes 8. All over x minus 2. Differentiate it. 1, Abi. Because 2 is minus 2 is 0. So derivative of x is 1. So you cannot differentiate further so as not to get undefined. So now you use your replacement theorem this time. This 2 times x2 minus 8 all over 1. So this is 4 minus 8. Therefore, the value is minus 4. That means this one is not that the limit does not exist. You can definitely use the L'Hopital's theorem and arrive at your limit. Any question on this? Is there any question?
Please, can you re-explain? My network got stopped while you started explaining.
Okay.
Thank you.
Let me, instead of re-explaining, let me take another example. If you take x to 4 for this function, 3x cubed plus 2x squared minus 7x minus 2 all over 4x, okay, all over 2x minus 8. Do you agree with me that if you just use the normal replacement theorem, that is replacing the x with 4, everything at the top still makes sense. But look at the denominator, you'll be having 2 times 4 minus 8. And 2 times 4 is already 8. That's 8 minus 8. Having 8 minus 8 under means you have something all over 0. All over 0 turns your problem undefined. And an undefined problem doesn't have a solution. So what do? Use the L'Hopital's theorem. How? Differentiate the numerator, differentiate the denominator. Keep differentiating until you cannot differentiate the denominator again. That is, if you differentiate the denominator, you are going to get 0. That's when you stop, because you don't want to get the 0. Now let us do that. I'll still have my limit x to 4, 3x cubed, differentiate it. You can do that, right? Dominion. So 3x cubed, I was something in, that's one. So this is 3 times 3, 29, Jerry. 9x raised to power 2 plus 2x squared is 2 times 2, 4x minus 7x, derivative is 7 all over differentiate 2x minus 8. That is ordinary 2. Now I've achieved something that I can't get 0 I've achieved something that I will only get 0 if I keep differentiating. So I have to stop there and now replace. And I can't get 0 if I use my replacement theorem now. So this is now 9 times 4 squared plus 4 times 4 minus 7 all over 2. So this is 9 times 36 plus 4 times 4 minus 7 all over 2. So 9 times 36 is going to give me 334. So 334 plus, please let me confirm it, am I right? 16 minus 7. 9 times 36. All over 2.
Should that not be 351?
Yeah, the network is...
That should be 351.
351.
51.
9 times 36.
51. 351. That's what it's supposed to be.
9 times 36. 350. Okay.
324.
Coming, I don't want to agree with that answer. So maybe 9 times 36.
324.
It is 324. 9 times 36. So it's not 334 as well. I got 334. I wrote 334. So it is 324. Now I have 324 plus 16 minus 7 all over 2. So this is 340 minus 7. That's 333 all over 2. So, and that's the case. This is going to give me what? 166.5 as the value of what? The value of this limit as x approaches 4. So, in essence, what L'Hopital's theorem is telling us is that we can always differentiate it and keep differentiating and keep differentiating until we get a value where we cannot differentiate it again. I mean, where we cannot differentiate the denominator again. And if we differentiate that denominator, we are going to get 0. So we will not differentiate it again, and that will be where we will do our evaluation. So that is what L'Hopital's theorem states. With this now, in the next class, we'll be entering pure calculus like that. The one that was explained at the beginning of the material. So we'll be taking that and we'll keep moving. And may God help us. Please, any question from anyone? Will there be any question? Any question from everything we've done on that stuff?
No question.
All right. Mrs. Bayode, Stephen.